Hello, can you hear me?
Hi, sir, we can hear you.
Okay. Any feedback from the last class? Any questions from last class? No. Okay. So today we are going for the derivation of the Rayleigh equation. Okay. So the first thing is that, uh, like for example, first we take the u as the u of t. The u is a function of the, and definitely u will be function of the x, y, and z. Okay. So it's a function of the time. So it's like a velocity at any instant. Okay. So with the time, its velocity is varying. So now we can divide the incidence velocity into the two components, the u bar and the u dash. Okay, u bar and u dash. U bar is the average velocity or mean velocity, and the u dash is the incidence velocity or the fluctuating component of the velocity. Okay, so this u is equal to the u bar plus a u dash. Okay. So, for example, if I'm taking the data at the one point in the, like, for example, for the flat plate and flow, and that flow is turbulent. So, it at the some point, if I take data, this data might be like is varying in the time as well, and as well as locally it's varying. So, it's in this case, the u bar will also be function of time. Okay, that is the transient velocity function. But at the same time, this velocity is also varying around its mean value. So any change in the mean value is called the fluctuating velocity. Okay, that is a u bar. So this change from the red line to the blue line, the blue velocity and the red line, actually this change is the fluctuating component. Okay, so the actual velocity is this one, and every velocity red color, and the difference between the blue and the red color is the fluctuating component. So that we can put in this way. Okay, now by definition of the, you can see here, if you zoom the area, you can see the u bar and u dash. U dash is the difference between the mean velocity and the actual velocity. Okay, that is in the blue color. Okay. Okay, so I can define the mean velocity as the average of the velocity with respect to like a time. If I multiply the time and then divide by the whole time. So if I integrate from time to t plus delta t, that is between these two locations, within this interval. Okay, and this can be true for the complete time step also. Okay, from beginning to the end. So this time is we are integrating this time, this function, the u with respect to dt, and from time t, starting time is t, and end time is the t plus delta t. And then if you integrate from the integration summation of the all the values, so then we divide by the delta t. That's a time interval here, and I will get the average velocity for that particular interval. Okay, this is the definition of the u mean or the u bar. And the fluctuating component, you can see it's a difference between the actual velocity and the mean velocity. Okay, so these are some handmade notes that I actually created. So this is the mean velocity that I'm drawing here, and the fluctuating component, that is like a difference between the velocity function, that is the instantaneous velocity, minus the u mean. This is over here. Okay, and definition, same definition I also put over here. This is called the Reynolds averaging. Okay. Okay, so this is if I integrate equation and then divide by the time for the whole interval, I will be getting the single value. Okay, not the local, u bar, but I'm going to get the one single value that is going to be steady state in the time domain. Okay, so that can also be done. So if I want to solve the problem as a steady state, then I have to average out data on the whole time scale. Okay, from the beginning to the final. But when I talk about the ensemble average or the Reynolds averaging, actually I'm talking about the averaging for a very low, like a very small time step. Okay. So if I want to make the problem a steady state, then I have to average data for the whole time, whatever time it is. Is clear? Okay, so here I've taken the different points and I just average them out. So this will be averaging of the whole domain. Okay, So that is called the spatial averaging. Okay, this is like average velocity I'm getting for the whole geometry, whole domain. That's a spatial averaging. Okay, this average, the spatial averaging is like is going to give you one single velocity. Okay, so I'm talking about the nonce averaging and the time averaging that is shown here. Okay, now let's move forward and start with the two equations. One is the x momentum equation and one is the continuity equation. Continuity equation is the conservation of mass, and the x momentum equation is the conservation of the momentum is x in the x direction. Okay, so the same definition again with we have here. We have the like a mean velocity, we have the fluctuating component, and this is the average velocity for the like for the whole time interval. Okay, and because the overall velocity is not showing the any transient behavior, so we can assume this is going to be our mean velocity for the whole domain, for the whole time interval. Okay, so what we have is that we have the change of velocity with respect to x and velocity in the y direction with respect to the u component and v component. This is actually telling you that we have the mass is conserved. Then we have the change of velocity with respect to the time. Then we have the convection terms. These are convection terms. Convection terms are different from the time terms. So how the convection works actually, our convective terms work. So convective term actually, for example, I know that on the same point, it's the same point, and I took data at the time t1, and then I took the data at the time t2. If there's some difference in the velocity, okay, so let's say the u2 minus u1 is there's some differences there, then I divide by the delta t time 1 minus time t2, and the limiting case is that the delta t is very, very small. So this is going to be the du by dt. Okay, so same point, but two on the two different time instance. Okay, that is going to be the du by dt. This is the change of the velocity with respect to time, but on the same location, exactly same location. But this term actually is a convective term. This, what does it mean? It means that we are having the velocity at the one point. This is like a location x1, and velocity is a u1. Second point is at the x2, and velocity is the u2. Now, if there's difference in the velocities, then we can like determine the velocity change as a u2 minus u1, or whatever value is greater, you have to put first, and then divided by the x2 minus x, and this is delta x. So the limiting case for derivative is that the delta x tend to 0, and this is going to be the du by dx. Okay, so now where this will happen now, this is change of velocity with respect to the location, not with the time. Okay, this du by dt actually is an acceleration, right? This is acceleration, but this is not acceleration. This is a change of velocity from one location to second location. So where this happens in the case of nozzle, for example. There's one example here. So velocity here on this point and this point are different because of the convergence effects. Okay, so the x location is different and the velocity is also different. Okay, but in simple pipe, velocity after when the flow is fully developed, velocity will not change. In that case, the convection terms will not be there actually. Okay, convection term in the x direction will not be there, but definitely in the normal direction, because there's a change of velocity, that term will be there, but not in the axial direction. Axial direction actually is the main term that is going to give you the acceleration sense. Okay, any questions? Any questions? No questions? Everything is clear?
Yes, you can proceed.
Okay. Okay, so let me check the comment. Okay, everything is clear. Okay, thank you. Okay, so now what we are doing is that actually now this is the these velocities are actually are the instantaneous velocities, means that they are the following this trend. Okay, so what we are doing here is that in the range, what we are doing is that we are actually averaging the velocity, so that we now this depends on the averaging like interval. So this is average velocity here, and any change in the velocity from the mean value is the fluctuating component. That is the u bar. So this is a u dash and u bar. This is a u bar. So u bar plus u dash is equal to the u of t. Okay. Now, thing is that the U bar, now right now it's a constant value, single value, but this can also be varying. For example, this can be varying in this way. For example, in case of water shedding behind the cylinder, their velocity is not constant, but maybe it's changing in this sense also. That's also transient behavior. Okay, its mean value, I'm talking about the mean value, not the mean value. If I average out them for the whole time, then I would be ending up with a one single value of velocity. That is like a steady state case. But actually, what is happening here is that on the different, in the water shedding, the velocity will increase and decrease on the one side, then decrease on the other side. But locally, velocity will also be varying. That is same behavior here. Okay, and that's not a constant actually. As I told you, turbulence is not a deterministic quantity. It means that it's not a constant change across the mean value. This can be like here, maybe there. But when we are talking about turbulence modeling, what we are doing is that we are saying that the change is constant. Okay, that's our approximation, but that will work very well. So at any point, the difference here, this is the your mean value. Okay, because actual value was this one. The black color was the u of t, instantaneous velocity. So what we did is that we divided into two components: this mean velocity and the change. Not this value now. Not no more this value. We are like adding the change here, the u bar. Okay, so this actually we are saying now this is representing the u of t. So this is already approximation. So that's why turbulence models, any turbulence model will not be 100% accurate based on the rents or U rents. So we are already making the assumptions here that turbulence is like a constant change is there, but actually the change is not constant. Okay, so this is one approximation turbulence modeling, and that's why we are saying that there is no universal turbulence model that can predict everything very accurately. This is the reason actually. Okay. So now what we are going to do here is that we are going to convert every value here into the u bar plus u dash, okay, in continuity equation and momentum equation. And then we see that where we ended up. Okay, so let's do this thing. And we are going to see the some rules here for the velocity in the two direction, u and v, and the pressure here as well. So u in the this is velocity in the x direction is the same as the equal to the u bar plus u dash, and v is equal to v bar plus v dash, and p is equal to p bar and the p dash. Okay, and if I want to have the any function that is a function of x and t, so if I want to get the average velocity, that is this capital F is actually a sign that we are having the average velocity of the this small f. Okay, this is equal to the 1 upon t. This is a time interval, and from 0 to t, f of x t dt. Okay, so apply this bar on all the equations here. Okay, and then put the this u into the these terms, u into the u bar plus u dash, v is equal to v bar plus v dash, and p is equal to p bar and the p dash. So I'm just averaging everything here. This is a like a Reynolds averaging. Okay, so what we are going to be seeing here, that if I take example of one term here, that is a du by dx, partial derivative of u with respect to x. So the its bar, its averaging will be based on this definition. Okay, this is equal to 1 upon t. This is a time interval of maybe a small time interval. This can be for the everything, but in this case, for example, here, this is the time interval for the whole time interval. But if I going for this way, then maybe we are averaging for the small time steps. Okay, clear? So in this case, 1 upon t. Now this is from the basic definition. I'm not directly applying some formula. I'm talking about the basic definition. So this is 1 upon t, and I can write down the u as a two form components, u bar plus u dash, and d by delta x, okay, and dt. So this is equal to the, now we can simplify the terms, and this is ending up like we have the derivative of u and derivative of u bar and derivative of the u dash. Okay, so we know that the average of average will again be a same average, same value. Okay, but the average of the fluctuating component will be 0. Why so? Why so? If I get the average of the fluctuating component, why it's a 0? Because some values are the positive and some values are negative. And I told you that in turbulence modeling, we are assuming that the change is constant. So like a small change or bigger change, they will be equal changes. Okay. So instead of in this way, what we are assuming is that the turbulence modeling assumes this thing. average change, like a same change. So if I have a change of the 1 meter per second here, and on the bottom side, I have the change of the 1 meter per second for the one cycle. So if I average out, so this will be 1 plus minus 1 divided by 2 is equal to 0.2 is equal to 0. So the average of the average of the change will be 0. Okay. Average of the fluctuating component will be 0. So definition is there that the change of change will be same thing. Okay. U bar is equal to same U bar, but the fluctuating component change will be equal to 0. So it means that if I put the terms here, these terms here, this term will be ended up with the only single term here. Okay. And we are applying this rule that the A plus B whole bar is equal to A bar plus B bar. But if there's a constant, then the constant will be outside, and only on the that is important term, that is like a vector quantity, will have the this average quantity. But if I have the dot product, then both terms will have the averaging, and we have the dot product between them. Okay. It means that the continuity equation will remain the same equation. Only thing is that now what changes here, that we don't have the fluctuating component. Okay. We don't have any fluctuating component. So the mean velocity will be used in the continuity equation. This is like a very important like a derivation here, and the finding is that the mean velocity is important, that is going to drive our flow rate. Okay. So and then if I put the average sign on the whole equation for the uh, what we call the momentum equation. And here what I'm assuming is that we don't have any transient component. Flow is a steady state. Okay. So and why it is so? Because the velocity, if the change of the time with respect to time, that is equal to the same value. So this component is going to be the 0 for this case actually. Okay. But for this case, I will be able to, I should be solving the U-Rance actually, because my average velocity is also function of the time. That's a separate thing, but right now we are assuming flow steady state, and we end up with like a no term for the transient value. Okay. Okay, so now we are left with the two convection terms and the one pressure gradient, and one term that is on the right side. This term is here. Okay, this is the actually a shear stress. There were three terms here. That is like partial u by partial x to second derivative, and partial u 2 by partial z square. Okay. But it is found that in the Navier equations, the normal stresses, this is normal stress actually. The normal stresses are actually, this is going to be the, sorry, partial v by partial y square and partial w by partial z square. The normal stresses, they have the very small like a component or very small magnitude as compared to shear stress. So that's why we can ignore them based on the magnitude analysis. Okay. That's why like if you go to the some theory of the fluid dynamics, you will see that these terms will be ignored because they have the very less importance. Okay. So what we have is that we are ended up with this equation here. Now we are going to divide them into the multiple terms here. Okay. So what we are doing is that we are applying the some transformation here. So what is transformation is that what I'm doing is that I'm taking this term here. This is like a convective term. So I'm saying that the u du by dx plus v du by dy, I can write it down as the partial second derivative, as partial derivative of u square divided by x. So why this is so? Why this is so? See, d delta u square upon delta x will be equal to the 2. Okay, power will be there, and this will be the 2u du by dx. Okay. And similarly, I can apply the multiplication rule or the for the derivatives, that is the u and the du by dv by dx plus v, that is we take the keep the one constant and second part derivative, then second term constant, derivative of first term. Okay, put the deltas here. So if we simplify, you will end up with the this thing. Okay. Okay, so we get the equation like this. Now see, uh, what is this? This is equal to the what? Can anybody tell me what is this thing? This term. What is this term? Anybody? This term is the
Continuity equation?
Yes, continuity equation, by conservation of the continuity equation, this term will be equal to 0. Okay, this is very true from the equation here, right? And because this is same equation as with the bar also, it means that this term will be 0. Okay, this term is 0. So even in the with the bar also, this term will be 0. So this term is 0. So we can write down this term as the partial second derivative, partial u square upon partial x, and partial u into v upon divided by the partial x. Okay. So now I'm starting with this term here, the first term here. So I'm putting that u as a u bar plus u square, u dash. So now I can put them in this way, okay, and put the bar there. So after simplifying, and see here that the any term that is going to be so this is we end up with this second derivative here, second derivative of this term here, okay. So see here that any change with the mean value and this term here, okay, this term here, this value will be 0. Okay, by rules of the derivative, that the change with respect to the let me guess it. This is equal to the u bar and u dash, and these terms we are cancelling out. Okay, I need to see this is how they are cancelling out, because maybe the negative sign is there, or there's some rule is there. So I don't remember right now. I just forget. Okay, so sorry for this thing. Okay, so we ended with these two terms. Okay, so now if I put the bar, what will happen is that this will be the 2u bar into du by dx, and this will be the like a delta and the u dash square and bar divided by delta x. Okay. Okay, so now if I go for this this term here, which is a duv, this term, okay, sorry, this term, okay, this term, second term, okay. So I can write it down as u is equal to u bar plus u dash, and the v is a v bar plus v dash. So now I can write it down as multiplying them. So I can end up with u dash, u bar, and the u bar. See here. Can you take a 5 minutes break? Something is making me confused. Some like a
Yes, sir.
okay.
Okay, sir. Okay.
We are going to come back after 10 minutes. Okay.
Okay, after
Okay.
10 minutes.
Okay. 10 minutes.